Hi, we now come to part D, the last part of this particular unit describing application structure, where we'll finish a discussion of the second set of features and conclude with the third set. So the first part of this little lesson is on aspects of the second set of features where we introduce global and local machine learning. So this is looking at a little different aspect of how the data is processed, namely that it's looking at the particular algorithms that are being used. And as we stressed, there's a pretty important difference between global and local machine learning. Global machine learning means you better take your machine learning algorithm and write a brilliant parallel version of it. Local machine learning says you still have a very difficult machine learning algorithm and maybe even more challenging than before, but you don't have to parallelize it because you're parallel over items. Namely, if you're running it over images, you're parallel over images. Within each image, you run effectively the sequential machine learning on each image. And of course, that corresponds to pleasingly parallel applications, as we discussed. When we come to iterative MapReduce, Exascale Global Optimization, expectation maximization, those algorithms tend to be global. Although you could have EM applied locally, but typically we're talking about global, the global case. These require non-trivial parallel algorithms, and they're both the algorithm itself and implementing it are often non-trivial. And of course, machine learning, as I've stressed, is sort of a very broadly applicable. It describes things like classification, which we've already introduced separately. And there's also what we might call domain-specific analysis, which tends not to be called machine learning. It's sometimes, like in the case of the radar-specific algorithms that process radar data, that's called signal processing, although it's not really that different from machine learning at some very, very high level, because it's taking data, applying algorithms to it, and converting it into meaningful information. It will use things like fast Fourier transforms and components that are components of many machine learning algorithms. We of course have expectation maximizations, a well-known characteristic of many of these algorithms, iterative. And you have two steps, the E step and the M step, and they each calculate new values for the subset of the variables fixing the other subset. And it's all designed to cope with the problem that you have typically an iterative algorithm where each iteration is nonlinear. You have to optimize nonlinearly, and you can't do it. So you have to break it up into linear steps. And of course, this is by definition a heuristic and can be done in many ways. And you have trade-offs between execution time and quality of the result. In this broad area, there's a special case we've already mentioned called graphs, which are really just saying that the entities we're dealing with, like people, are not connected in some simple regular fashion, but have a complex connection where that complex connection is critical to the algorithm. As I pointed out earlier, that's non-trivial for parallel computing, because where the links between graph nodes crosses processor boundaries, you have to do communication. So I've introduced this exotic term, Exascale Global Optimization, and I call it that because somehow in today's world we want to use exascale machines. It's globally optimized because it corresponds to a characteristic problem where you take some huge collection of things, documents or images or what have you, and then you find you optimize something. The weights of a neural network, the positions of cameras or something like that, and or the assignment of documents to topics. So it comes to some sort of giant maximum likelihood method or chi-squared fit, where you have a huge sum over items, which items are distributed across processors. And then we have also a whole set of classic algorithms for optimizing this. And that's where we come to clustering, community detection, which are roughly the same thing. Mixture models, which are almost as mixture models, topics, clustering are really very similar. Multidimensional scaling and deep learning are rather different from those two. PageRank is an example of an important global algorithm. It sort of made Google famous, and it corresponds to finding the largest, the eigenvector with largest eigenvalue of a matrix, and it's sort of parallel linear algebra. If you go to Mahout, which is the famous library, you'll find that many of those algorithms are not properly parallelized, partly because MapReduce doesn't do very well because of its performance problems, and partly because the parallelism is sometimes unclear. The Spark-based library MLlib has got a better quality, possibly better set of approaches, but not as broad. There are some algorithms like support vector machines and hidden Markov methods, which don't seem to have a large parallel literature, and it's not quite clear to me why that is, whether it's the algorithm doesn't properly scale or whether maybe it's just not useful. There are lots of papers on parallel graph algorithms, which we will not go through in this class. So as we hear, this sort of stresses again what EGO is. It's representing an artificial global machine learning problem phrased as a giant optimization over many variables. It was invented at a meeting I went to organized by Argonne-Chicago. And as I say, it involves typically chi-squared or maximum likelihood. You end up with a bunch of terms, each of which is usually like in chi-squared positive. And you have to minimize that sum of terms with respect to the variables. And there are essentially always nonlinear optimizations, and there are never any exact methods. You have to use some approximation, such as the EM method. This is, of course, very different from rule-based approaches to artificial intelligence. You're not, you're optimizing something, some continuous function, and it's actually interesting because this is essentially intrinsically probabilistic. You can actually properly minimize the sum of a billion terms. But you can't actually, of course, apply a billion rules because the rules will be in conflict. That's the key idea of chi-squared or maximum likelihood. You're taking a bunch of things and finding the trade-off between them when you sum them up as to which minimizes the total sum. We will go through multidimensional scaling later on, where you have a sum over similarities. For your endpoints, it's n squared over 2 such sums, and you minimize the difference between the square of the difference with some weight between the similarity in the original space and the similarity into the space in which you're mapping. Another example is, of course, there's information retrieval, where you might do, say, for Google News, take the world's news items and find the best possible set of topics implied by them. Those are sometimes called latent factors. What's the hidden classification of within a set of data? Now we come to the third set of features, and discussion of them. So we have here workflow, which actually is effectively present. I put this in 51 because it's essentially present in all applications. Because workflow is how you link jobs together, and it's very difficult to find any application which hasn't got more than one job. Geographical information systems are very important. It comes in any application such as those in Earth, polar and environmental science, where you have things displayed on the Earth, geotagged information. There you have these companies like Esri, modern web-based systems like Virtual Earth from Microsoft and Google Earth. There are a whole bunch of systems here. These are open source systems, GeoServer, Minnesota Map Server. So there's a lot of possible GIS systems. High performance computing is important because several of those applications, like the astrophysics application and the climate application, involve simulations. and you need to take those simulations, which then form data. The results of the simulations are data. In the case of astrophysics and climate, that data is actually in 3 or 4 dimensions and can be thought of as actually put on GIS if you wanted to, but they can be visualized or looked at, and then you can find features of those simulations, like particle trajectories or trends of turbulence or aspect of the climate. And the last category is, so this is HPC for its data. The last category is agents. Agents are a simulation technology, and they're used especially for macros, where the simulation involves some complicated entities for which one can't use differential equations and things like that directly as you do in simulations, but rather you have to use different approaches, which are so-called event-driven simulations and things like that. You use these in things like simulations of city for transport studies or spreads of information in complex systems. So let's look at these categories. The first one is the Geographical Information System category, GIS. And as I pointed out, there are lots of use cases which are Earth-related. And the two most obvious are some of the physics, not all of them, most of the astronomy, all of the Earth and polar science, the defense applications. You always fight battles on the real Earth. Those tend to all be GIS-related. And I say we need to use a GIS system, which is available from these different places. There is a consortium called the Open Geospatial Consortium, which has set a lot of important standards so that the data is known how to be stored, so the data can be displayed effectively in all these different approaches, all these different GISs. So this provides interoperability between different data sets and different display systems. Here's some examples of displays. This is sort of 3D displays. I mean, actually, if you do science, then here we have a 3D display of a nanomaterial. So that's got optimized display methodologies for that type of science. So this is an example. This comes back to our HPC case, which we'll do later on. Here we have a geographical information system displaying global positioning sensors. Here we have a whole bunch of sensors displayed on a map, and then if you click the sensor, you'll get this information like you do here, telling you what that sensor has done and what is revealed about the world. Here's an example of a GIS and information fusion. It's a robot, or actually it's a Internet of Things application. We have Lego robots trundling around, controlled by the cloud, and then they're displayed. Actually, they're in different places. Here's one in Silicon Valley and one in Hong Kong, and they're talking to each other and making decisions. And over here we have the control interface telling us which of the various devices, the RFID sensor or the Tribot, which is a particular robot, which we're trying to control. So this is an example of an Internet of Things dashboard, and it's using GIS because these robots are sitting in three-dimensional space-time, or four-dimensional space-time. Now we come back to the HPC. We sort of somewhat illustrated that for GIS because in some sense HPC often is used in simulating the Earth, or in the case we actually showed, materials, which are three-dimensional naturally. And of course we have here the fact that simulations produce visualizations which need to be looked at. Here we have airflow, here we have climate, here we have, I think, molecular dynamics. And a key interesting number is that if you run an exascale supercomputer, it's going to produce visualizations with data measured in petabytes per second. So those are big numbers. So you have to have a lot, you have to worry a lot when you come to exascale systems about how you cope with the visualization. Okay, so now we have agent-based modeling. And as I said, agents are just a way of doing simulations when you have a complicated object as the entity. If your simulation consists of peoples and cars, as it might do for a traffic simulation, those peoples and cars are not like a point in the differential equation with their characteristic defined by 4 numbers, the weights of its interaction with its neighbors or something like that. Rather, it has a very complex set of rules governing the action, what the car does when it hits another car, when it stops at a light, and so on. So those rules are embodied in the agent. So agents are a very important way of doing simulation for systems formed from complex nodes. And often those nodes effectively have graphs showing them how they interact with other nodes. And you can you use various simulation methodologies. The most general is called an event-driven simulation, but that tends to be rather slow and not easy to parallelize. And the people working in these areas have developed much faster methods than which effectively avoid the sequentialization of the event-driven model. However, this is not a dominant, this is only seen in a few cases. In the use cases, it corresponds to the modeling of society and the spread of information and things like that. And then we come to the final slide. Hello, here is the last slide. It describes what these 4 parts of this unit, the 4 lessons within this unit have described. We introduced the NIST Big Data Initiative, describing its 5 subgroups. One of the subgroups looked at taxonomies and defined data science and big data, which was pretty interesting. Another did reference architecture. Another did futures, and another did a great job on security and privacy. Then after that, we discussed we listed the applications, but we didn't really describe each of them in detail. Rather, we discussed where they got their parallelism, because all of these are running on these horizontal scalable platforms, and the parallelism is gotten by dividing items of various sorts from people through electronic medical records across the machines. And we then also discussed the features, such as local machine learning or workflow or streaming or HPC simulations of these applications. And we then looked at those features and described each of them in modest detail. We'll do some of them in more detail in the next slide set. As you could see, I particularly like global machine learning, but stressed that actually local machine learning was in some sense more common. There are more local machine learning cases where each item has machine learning applied separately. So now we get on to, this is the end of this particular unit, and I look forward to starting the next unit, which goes through in a little more detail some of the issues of the features. Thank you.